Today, I'm gonna introduce our work in this ICASSP, and this work is mainly talk about a demonstration of quantum circuit learning for broken command recognition. And this is our demonstration team, and this is Huck from Georgia Tech, Jun also from Georgia Tech, Dan from Blue Haven National Lab, and Pingyu IBM Research. Our paper decentralizing will be also presenting in the ICASSP main value. So you can also check more experimental detail in the other session. So this session is trying to provide an interactive demonstration and the code implementation on the idea of quantum machine learning and speech processing. And we also want to thank our advisors, Professor Qinghui Li, Professor Marco, and Professor Ma. So this is our show and tell schedule today. So first I will introduce quantum circuit learning, and then I will give our first demonstration of the encode acoustic features with quantum circuit. And then will be our second demonstration of training a hyper-classical quantum model for speech processing. And finally will be some overview and future discussion. So first, what is quantum machine learning? So when we really look at the term of machine learning or statistical learning, we can see first we want to determine what kind of data we want to process. They can be the classic data like the phoneme or speech, or it can be some physical measurement, for example, the gravity wave as a quantum format. So with this kind of data definition, we can also witness some algorithm-wise definition, like the classic type of algorithm like simple vector machine or neural network. They can use this real value or even like the complex value conversion. But for quantum state, like the quantum Boltzmann machine or like the matrix-wise computation, like the kernel masses, they can be using this algorithm purely quantum. But one idea is to trying to encode some classic data like the speech or image and then use part of the algorithm as quantum. And why this become important? Because right now, with the power of deep representation learning, increasing the data scale will really help for having a more robust and accurate model. And when we really look at the advantage of quantum computing for this example, we can see these both vector presentation. You can see even in the x coordinate and y coordinate, we also have the z. And then in this probability ball, you can do this encoding and have a rich representation. So this is one of the advantage, like the large representation space in the Hilbert space. And then also have some memory and capacity advantage for solving some NP-hard problem as recent demonstration. And for today, we introduce quantum circuit learning. You can think of they use parameter shifting to train a model end-to-end. And then by using parameter shifting, the quantum circuit will first have an encoder space to encode this classic data to quantum state. They can use amplitude encoding or angle encoding. And then with a certain gate with hyperparameter like the rotation, they will convert the vector to one specific angle in the high dimension space. And then we do the decoding and convert this quantum data to classic value to calculate the error and to minimize the cost. And then you can have a quantum machine learning model as quantum classic circuit learning. So one advantage is they use gradient propagate. So you can combine with this neural network and train all the model end to end. And from the implementation perspective, this kind of model will be also realistic. So right now we don't have really large scale quantum computer. By using this quantum circuit learning, even you have a quantum computer like like you can have in the IBM Acoustic or IBM QHub, like have 5 qubit. So even you have this kind of quantum computer, they requires no to really little quantum error correction, and also they requires few qubits, so you don't have a lot of resource, and they can democratize this experiment. And if we really look into this quantum circuit learning, so how it works. So firstly, for example, if we have a certain value in the NumPy format, the first idea is use amplitude or kind of encoding to initialize this quantum state, like the initializing and reset here. And then we have this quantum gate. This gate just like the layer in the neural network and equipped with these hyperparameters. Finally, we do this measurement, and the measurement will have this quantum gate with this wiring. And finally, with this wiring, you have your target output. You calculate this target output as a loss equivalent, and then trying to minimize this output. And this computing process, in this example, you can see they only require 3 qubits and 2 classic bits. So this really empowered this quantum machine learning in practice in our era. So in our ICASSP presentation, we propose quantum convolution, especially for speech command recognition. So the idea is a local user, if they really care about this privacy, so we use the idea of vertical further learning. So you do your feature processing in the cloud computing, and after you do this feature extraction, you feed this randomized like feature to a like neural network model. For example, if you have this quantum machine on the cloud, you can extract MFCC or Mail spectrum, and you feed into a layer by this quantum circuit calling quantum convolution layer, and then you have this convolutional features feeding to the RNN attention model for different acoustic modeling tasks. So you can classify the class or provide CTC-based like character level prediction in our implementation. So the idea is you have your mail scale features, and then for each mail scale feature, you just do a 2x2 convolution with this quantum circuit. So it's still like convolution, but you use quantum circuit to do this like feature converting. And then by this converting, for each channel, they'll have a different representation. And we use a random circuit, so we can avoid some challenge like parameter leakage and trying to improve the privacy and data protection. So this is in our experiment. This is one of the speech command of on. So you can see for each channel, they learn different high level or low levels like acoustic feature. For example, they can learn the age of this like sequence in the spectrum domain, but they can also learn some low frequency like the features, and some of these like early or the late temporal feature from this acoustic model. And we also want to appreciate Chao-Han AI, the open source this QCNN tutorial, and Andrea Marie in 2020. So here I'm gonna introduce our first demonstration is encoded acoustic feature with quantum circuit. So we provide a link here, but you can also provide your feedback in our online session during the ICASSP. So here is the structure. First, you can upload or record a speech command, and then you can define a quantum circuit, and finally you can see how this quantum encoded acoustic feature would be. So here it is. So first, you will have to install some required like audio package, and then you can record your sound, or you can upload just one speech command for 1 second. And remember, it's a single channel version, so it depends on your microphone. So I have a pre-recorded one. It's a yes, or we can have a hello here. Hello. Hello. So we have hello now as a good demonstration. And you can see the male spectrum here about my hello, and you can have your hello also. And then you have to define your quantum circuit layer. And the quantum circuit layer is trying to, first you have to define your backend simulation. So you can use the quantum machine especially, or you can use a CPU simulation. Or for Google, they also provide like the tensor-wise like processing unit to accelerate this simulation. But right now we use CPU on the Google Colab. And then you can define your random algorithm for privacy preserving as a random quantum circuit. And this quantum circuit is trying to decode the feature map as a 2x2 convolution with this circuit. And then finally you'll pick up this like this kind of a 2x2 mapping over all the feature map in this like process. How would it look like? You can see the process right now. We just feed our just recorded like the Mills feature to this quantum convolution function, and then you got your feature here. And let's see some visualization. So yeah, we have 4 channel because it's a 2x2 convolution. Okay, it's my yes. All right, so it's the original mirror feature. You can see each channel learn different kind of the intensities over here, over here, over here, over here. So it depends on the microphone you record it, and it also depends on the random parameter you select. But eventually, if you have a lot of this kind of feature, they do learn kind of the shape or some informatic feature by channel. And we also have a tutorial in EJKI this year. Okay, and then let's look at our second demonstration. Our second demonstration is for how to train a QCNN speech recognition model. So first, with this quantum convolution feature, have found the Google speech command, and then you can train a classification model, or you can train a CTC model. Even this can be used for large-scale speech recognition if you use it with liberal speech. And after you click the link here, you can have our second demonstration. First, we have to clone our get repo and install some required stuff. And finally, you can be training the model. So we use attention RN, so you can see the RN here and the self-attention here. And then here is the training process. And eventually we have accuracy around 86 with 30 apples. Yeah, so I pre-process these features so you don't have to extract by yourself. And then here is one of the feature model with more features. You can see with this quantum convolution, the model do learn some good feature and much rich feature according to the original speech features. And then you can also have the CTC model we provide here. If you really look at this ASR, large scale ASR, and then you can see how it works with our prediction model. All right, you can do the characterized or word level recognition with the quantum convolution. All right, so there is some final remark. So first, we open source all the implementation in this tutorial, and you can check our GitHub. And eventually, they'll have some quantum hardware solution recently, and you can use the simulator as we can. And we also appreciate a lot of effort in this community, and we also appreciate BNL to support our registration. And feel free to contact us for any collaboration, and I will be on the job market next year. So if you have some quantum machine learning or speech recognition or acoustic modeling job, feel free to contact me, or you just simply want to learn more about this work. So I think really appreciate today, and let's meet online